Hi, everybody. Welcome to Byte Ventures, where we deep dive into the marvels of technology. In today's case study, we'll discuss about Pinterest async computing platform with the revamped architecture, which help them manage millions of asynchronous workloads very efficiently. So without further ado, let's dive deep in. A little bit of background. What exactly is Pinterest? So Pinterest is a visual bookmarking and image sharing service or a social media. People use Pinterest to inspire the creativity, manage the designs, or any of the things that they want related to designs. Any piece of content, including an image with a description, is called a pins in terms of Pinterest. A collection of pins put together based on some kind of grouping structure, a theme, or whatever is called a pin board. And any Pinterest user who uses Pinterest in his daily life is called a pinner. Okay, the use cases. Why do we think that Pinterest as an image serving platform would need such a huge async computing framework or a platform? So talking about this, there has been a huge user base using Pinterest in their daily lives. They save their pins, share it across friends, which eventually leads to processing images in the background. They trigger some kind of actions which lead to thumbnail generations, or in some cases, the Pinterest as a platform would require to send some kind of updates to its spinners and all stuff, which would require different kind of background job processing, scheduled job processing, and they would need a platform to process all of this information. Back in 2015, Pinterest have made their then existing the synchronous job execution platform called PinLater, which has gotten huge popularity because of the kind of scale they supported. But with the increasing traffic and increasing user requirements, the PinLater service suffered a huge bottlenecks in different kind of ways. It faced a lot of scalability issues and it was not able to scale properly with increasing load. The resource utilization of the hardware was getting much lower because a lot of time was getting wasted in bad design decisions. And third, the usability, which is developing or carving new features based on that has been becoming complicated because the way this framework or the platform was built in. This was the whole reason the Pinterest team decided to revamp their architecture and create something as Pacer, which would eventually solve the PinLater's bottlenecks and issues via better throughput, better resource utilizations, and all stuff. But before diving into Pacer, let's see what exactly was the architecture of PinLater and how did it solve the problem. So these are the clients. So that means anyone or any user who uses an Android app or iOS app or the website would be a client of the Pinterest platform. They indirectly, with their actions, trigger some kind of NQ events. That means they lead to some kind of generation of async jobs, which would be processed later in the time. These jobs would be NQ'd via a service called PinLater Thrift Service. So PinLater Thrift Service is a stateless distributed service developed as part of the PinLater platform, which would provide this NQ functionality and NQ these jobs into this particular store, which can be executed later. So this NQ request required a queue name to be specified because this thrift service would eventually take this queue name and put the job into this respective queue name. This had a data store connected because as this is a stateless service, all of the information should go at one go. That means whenever a client requests an asynchronous job to be executed, they provide a different kind of metadata or payloads, which we would need to store in the data store for later execution. As part of their GitHub repository, they provide two implementations for it, which is MySQL and Redis for the data store part. They have given multiple sharded configurations, and based on the requirements of a user, they can use any of that. And the last part is the worker nodes. The worker nodes were responsible for dequeuing or registering a DQ request to this thrift service, which would eventually go to the data store, find the jobs that are available, which needs to be processed, and assign them to these worker nodes. These worker nodes would process them and provide an ACK signal, a success or a failure, based on the results of the execution. And this eventually completed the whole architecture. That means they have this queue which they want to enqueue this data, though the user will not know it, but their actions will trigger it eventually. This would go to the data store. That means there has to be a queue to the data store mapping. Yes, you're correct. So each queue, according to this design, had a partition in all of the shards. That means, as I told you before, that there is multiple shards of this data store which they have designed. That means when there are like 3 shards, for example, and there are 2 queues, each of the shard will have 2 tables from the corresponding queues. Let's see an example. Suppose we have 3 shards. Let's say this is the 3rd shard instead of n, and there are 3 job queues that we have right now. So this job queue 1 will have a table in the 1st shard, will have a table in the 2nd shard, will have a table in the 3rd shard, and so on. This doesn't depend on the amount of data flowing in or amount of the traffic that they have, but they have to have present in all of the shards. This is one of the decisions which was serving initially, but this led to a huge problem that we're going to see further. Okay, let's see some of the problems that they faced as a platform. So thinking about the DQ request, okay, going back to the diagram. So this DQ request was fired or requested by this worker nodes. Whenever they fire this DQ request, which would eventually reach the thrift service, this thrift service would talk to the data store to get the available job, right? But think about this. As each queue had a partition in all of the shards, this thrift service would have to go and search through each shards to find the job. Pretty expensive, right? Because think about when there are multiple threads getting spawned and each of these threads are trying to access the same table in all of the shards, a lot of resources would be wasted in managing the locks and all stuff. That was a huge problem. The second thing was jobs from multiple queues were running in the same worker host. That means there was no way that we can say that, okay, this kind of job is assigned to this kind of worker, which would lead us that we could not optimize any of the queues because we don't know what kind of jobs we would get eventually. And the worst part, any bad queue would lead to affecting the whole cluster because it might take the whole cluster down and we would be affecting all of the operations. The third thing is the critical component of the thrift service. The thrift service was responsible for enqueuing and dequeuing both. So if any of the dequeuing logic failed, then the enqueue service is impacted as well. That means the client, which would be registering any kind of asynchronous job, would not be processing it because of the huge single point of failure. Introducing Pacer. So let's see how Pacer addressed some of the issues that were bottlenecks in the pin later service. It had the same structure. The client would register the enqueue request, and this request would eventually reach the thrift service. The thrift service would talk to the data store to store the metadata and the payload for each of these requests. But there are a couple of new things that were introduced after this point. The first of which is the DQ broker service. So the single point of enqueue and DQ was now separated to 2 different services. The pin letter thrift service is now responsible only for enqueue operations. All the enqueue operations come to here, they're stored to data store. This DQ broker service is responsible for dequeuing it. With the help of Helix and Apache Zookeeper, this DQ broker service implemented a very interesting design, wherein one kind of worker nodes was responsible for one partition of the queue. This would help them resolve the lock contention issues that they were facing earlier and would save them a lot of resource utilization problems. So if you don't know about Zookeeper, so Zookeeper is a configurations or a coordination management system which helps in managing the different configurations of a data distributed system. It provides distributed logs, watches, and all stuff to manage these things efficiently. Helix on top of Zookeeper is used to manage the life cycle of a distributed system. That means it manages the DB, it rebalances the resources in case there are more resources, less service requests, or less requests, or more requests or less resources, and stuff like that. It helped in making the system highly available and manages any kind of faults by spawning instances depending on the configurations that they have. Last but not least, the worker pool. The worker pool, which is used to query the thrift service in pin letter design, now queries the DQ broker service to get the job. And each of the worker pool has a dedicated worker nodes via Kubernetes, which is tunable, which is optimizable, because now that we know that, okay, this is getting assigned a particular kind of queues, we know that this will be helpful to optimize it. Let's see the architecture of Pacer. So Pacer had a client and a thrift server. The thrift server was responsible for enqueuing all of the jobs into different queues as per the request. And there is this data store. In this case, it's the MySQL cluster as per the example. And these smaller rectangles are the shards. So this is probably a shard 1 and shard 2 and so 3 and so on, right? As per the older design, a partition of the queue A has to be present in all of the shards, but not in this case. That means based on the traffic, based on the requirement, the partitions are created. And in this case, QA has 3 partitions, A1, A2, and A3. So QA has 3 partitions, A1, A2, and A3, which stores the required data. Similarly, QB has 3 partitions, B1, B2, and B3, and QC has 3 partitions, C1 and C2. So this is the map that is also stored, which helps them know that, okay, this queue has only 3 partitions and this is present in there. This is the DQ broker service, which is the stateful thing, which knows that, okay, this broker or this worker node would consume only the partition 1 of this. The other worker would consume only this partition of this. This worker C would consume only 1 partition of this, right? Which is present in shard 1. So now, based on this, there is no contention or there is no fighting for any resources, because now each one have a unique responsibility of dequeuing queue from a single place. That helped them solve a very bigger problem. And let's see how the other problems were tackled. Okay, we discussed this with the help of Helix and Zookeeper. The new platform, or the Pacer platform, removed the lock contention problem and eventually increased the resource utilization rates. With the help of dedicated worker host, the system has become more resilient. Think about this. When we have different worker hosts, any problems would not propagate to other kind of clusters. So now, previously, different kind of jobs were being processed by the same cluster. If any of the job queues were bad or faced some kind of failures, then all of the other job queues were impacted. But now that there is a dedicated worker host, we don't need to care about this problem anymore. And this has eventually increased the resiliency of the platform. Each type of job is executed in a tuned environment. And now that they're spawned via the Kubernetes cluster, we know that what kind of optimizations we can do to make this thing pretty much efficient. And last but not the least is the buffer implementation. The buffer implementation is done as part of the DQ broker service. So the DQ broker service implements some kind of buffer. So let's go back to the diagram. So this DQ broker service, while fetching the data store, maintains some kind of buffer, in-memory buffer service, so that whenever the request comes in from DQ, it doesn't need to query the data store every single time. So it can pre-fetch them and store them, so that whenever a worker comes and asks for QA data, or QA first partition data rather, it would give back from the QA first partition's buffer that they have stored. Obviously, to maintain the sanity of this service, they need to have an upper cap, and there is a lot of mechanism to store, evict which one is done, which one is not, and all stuff. But on a top level, it implemented um, the buffer service. The buffer service was very instrumental in reducing the DQ time. It get down to 1 millisecond. That means it was a huge improvement on the older kind of system. So yes, that is all I had. And this is how the Pacer platform eventually solved the bigger pain points that Pinlater was having. And that's all for today, guys. Let me know if you have any questions in the comment section. I will attach all of the official blog pages in the all the official documentation in the description below. Let me know any feedback or any questions. I'll be happy to answer them. Otherwise, have a nice day and see you in the next one.